On the northern coast of Vietnam, workers are standing ankle-deep in grey mud, pressing tree seedlings the width of a finger into the silt. Behind them, a concrete sea dike runs for kilometers, stained, cracked, patched with fresh cement. In front, nothing. Open water, the South China Sea. Typhoon season is weeks away. The seedlings are barely taller than a forearm, and the plan, the official, government-backed plan, is to use them to protect a coastline that has been flooding harder every year, destroying homes, farmland, and driving families from villages their grandparents built. That plan sounds embarrassing. It wasn't. This is what a coast looks like after the trees are gone. The workers pressing those seedlings into the mud are not environmentalists on a campaign. They are members of coastal communities who have watched their sea dike crumble at the same sections season after season. The same concrete faces, the same fresh cracks appearing where old repairs sit, the same maintenance crews returning to the same spots with the same materials, doing the same work that will need doing again within a few years. What you are looking at is not a coastline facing a new disaster. It is a coastline in a slow emergency that has been building for decades, while everyone involved assumed the problem was engineering, when the actual problem had been standing in the tidal water a few meters away, right up until the moment it was cut down. The dike was being asked to do something it was never designed to do alone. To understand that, you have to go back to the 1980s and through the 1990s and into the early 2000s. Along the coast of northern Vietnam, in provinces like Quang Ninh and Hai Phong, aquaculture was expanding rapidly. Shrimp farming, fish ponds. These were not acts of environmental recklessness. Families were trying to build sustainable income in a region where the sea was the primary economic resource. Government programs supported coastal development. And what stood between these communities and the South China Sea was a dense, ancient mangrove forest, gray-barked, tangle-rooted trees growing directly from the tidal mud, some belts stretching for hundreds of meters between the villages and the open water. Those forests were cleared, not out of hatred, not out of ignorance about what trees do in general. They were cleared because the shallow, brackish, sheltered tidal flats beneath them were precisely the environment that aquaculture ponds required. The mangroves came down, the ponds went in, and the concrete sea dike, which had always existed as the last line of defense behind a living buffer, was now the first thing the South China Sea touched at high tide during storms, during every typhoon that moved across the Gulf of Tonkin. For a while, nothing obviously catastrophic happened. The dike held. The ponds produced, communities built income, but the sea was now landing on concrete directly. Every tidal cycle, every seasonal surge, every storm, and concrete, unlike a living forest, does not adapt, grow, or repair the damage accumulating inside it. Here is what most people missed. Mangroves are not a wall. A wall stops something. A mangrove forest dissipates something, which is a fundamentally different engineering principle. Picture the root system of a mature mangrove stand. Thousands of curved prop roots per square meter, each one arching out from the trunk into the tidal water, creating a three-dimensional lattice that extends from the mudflat upward toward the canopy. When a wave enters the outer edge of that system, it does not hit a barrier and reflect. It enters a maze. The water has to move around roots, through root gaps, around more roots, losing energy to friction and turbulence with every meter it travels. A 4-meter storm wave entering the front edge of a mature mangrove belt is a different creature by the time it has moved 50 meters through that root structure. By 100 meters of mature forest, what was a wall of water has become something the concrete at the back was always designed to handle. The dike only needs to catch the leftover. Without the trees, it catches everything. Concrete fatigues. Under repeated wave loading, microfractures develop. Seawater penetrates those fractures, reaches the steel reinforcement, and begins the rusting process. The sections that have been patched once respond differently to stress than the original material around them, and the boundary between the old and the new becomes a recurring failure point. Communities in northern Vietnam's coastal provinces were noticing by the 1990s and the 2000s that their dike maintenance costs were climbing in ways that did not match normal infrastructure aging. The same sections failed repeatedly. Engineers were not doing substandard work. The concrete was not poor quality. The problem was that the dike had been left to carry a structural role it was never intended to carry, without the biological system that had been absorbing most of the load. Nobody initially connected this to the forest. How could they? The mangroves had been present for so long, for multiple generations, that they had become completely invisible as infrastructure. They were the trees by the water, the place where children played and fishermen worked. No engineer had ever formally measured how much wave energy they absorbed, because for as long as anyone could remember, those measurements had never needed to be taken. The protection simply existed. When the trees were gone, the deteriorating dike felt like normal concrete aging to the communities behind it. The increasing flood damage during typhoon season felt like intensifying weather, or bad luck, or something outside local control. The maintenance bills felt like the ordinary cost of living by the sea. This is the damaged baseline. The communities pouring money into those dike repairs were paying annually to approximate a level of protection the mangroves had been providing at no cost. What they experienced as normal, cracking concrete, escalating repair cycles, worsening flood risk, was not normal at all. It was the emergency the forest had been quietly preventing every day it stood. So someone said, "Plant the trees back." And the first response, the reasonable, practical, immediate response, was doubt. Can trees actually stop typhoon waves? These are not small waves. These are 4-meter storm surges hitting a coastline where homes and farmland and livelihoods are stacked behind a failing wall. A mangrove seedling is barely 30 centimeters tall. The dike it needs to protect runs for kilometers. How long would even a successful replanting take before it mattered? 5 years? 10? These communities could not wait for a forest to grow. But somebody tried anyway, and the first attempt failed. Early restoration efforts in some of the highest wave sections along the northern Vietnamese coast produced seedlings that the sea simply removed. The workers pressed them into the mud, and the tidal water pulled them back out. Young mangroves have almost no root structure in their first months. They need calm, low-energy conditions to give their roots time to anchor in the silt. In the very locations where mangrove loss had been most damaging to the dike, the most exposed, most heavily wave-impacted sections, the water conditions made it impossible for seedlings to survive. Communities and project managers who watched these early efforts wash away drew the logical conclusion: restoration cannot work here. The trees grew here once, but those conditions are gone. That conclusion kept the budget flowing toward concrete. But here is the trap. Mangroves need calm water to establish. Calm water in an exposed intertidal zone requires an existing mangrove belt to create it. The trees cannot grow in the places that need them most because those places do not yet have the conditions that established trees would produce. The system needed its own starting condition to restart, and that starting condition had been erased. It was a loop with no entry point. This was the real bottleneck. Not the species, not the ocean, not the damaged substrate. The bottleneck was a self-reinforcing absence, a system that could not start because it needed to already be running. The solution, when project teams found it, was not impressive to look at. In some restoration zones, workers began placing permeable breakwater structures offshore, simple fences built from bamboo poles or wooden stakes, driven into the tidal flat in rows, with enough spacing to slow incoming wave energy without stopping tidal flow altogether. These were not seawalls. They were not significant civil engineering. They were temporary, low-cost structures made from local materials, installed to do one specific and narrow thing: reduce wave turbulence in a small nearshore zone, just enough that mangrove seedlings planted behind them could survive their first growing season without being uprooted. They were not trying to build the whole forest. They were trying to give the forest a head start of about 1 season. It held. The first seedlings that established behind the bamboo fences did what mangroves do when conditions allow. Their prop roots spread laterally through the silt. Those roots captured sediment particles suspended in the water, gradually raising and stabilizing the mudflat around them. The slightly elevated, better anchored surface improved conditions for the next row of seedlings planted further out. That next row, once established, absorbed some wave energy of its own, creating slightly better conditions for the row beyond. The mangroves were now building their own growing environment, extending the protected zone outward with each successful planting cycle, requiring less additional intervention each season than the cycle before. The bamboo stakes had broken the loop. The forest was doing the rest. And then the numbers stopped looking small. Monitoring along protected stretches of the northern Vietnamese coastline produced a measurement that is worth stating plainly. On open coast, storm wave heights were recorded at approximately 4 meters. Behind restored mangrove belts, those same storm waves arrived at the dike face at approximately half a meter. 4 meters to half a meter. That single figure is what the entire restoration effort was building toward. According to NDC partnership documentation of this program, the reduction in wave energy reaching the dike translated into a reduction in dike maintenance costs of approximately $7.3 million per year along the protected stretches. $7.3 million. Every year. Not spent on concrete, let that number land. The provinces along northern Vietnam's coast had been spending heavily on dike maintenance for decades, season after season, patch after patch, section after section, because the biological system that made that maintenance manageable had been removed. When the trees returned, the maintenance burden did not decrease by a modest margin. It dropped dramatically. The concrete dike did not stop being necessary. It is still there, still the final physical barrier, still essential. But it is now doing what it was originally designed to do, acting as a last line behind a living buffer that has already absorbed most of the energy. The trees did not replace the engineering. They made the engineering survivable again. The Vietnam Red Cross, working through its restoration and coastal protection program in northeastern Vietnam and documented by Prepare Center, scaled this approach to approximately 9,000 hectares. The number of direct beneficiaries, coastal community members, now living behind restored mangrove belts rather than failing exposed concrete, reached around 350,000 people. That figure deserves its own moment. The project did not begin as a regional transformation. It began with workers in mud, bamboo stakes, and seedlings the width of a finger. It scaled because the mechanism worked, the costs were manageable, and the results were visible and measurable enough that agencies and communities could build a clear case. But then the story got stranger. Mangrove root systems are not just wave barriers and sediment traps, they are habitat. The same prop root maze that breaks wave energy is one of the most productive juvenile fish nursery environments in any tropical coastal system. Small fish find shelter in the root network, where structural complexity protects them from predators and concentrated organic material provides abundant food. Many commercial and subsistence fish species that support coastal livelihoods spend their juvenile phase in mangrove habitat before moving to open water as adults. As the mangrove belts in northern Vietnam's coastal provinces recovered and expanded, local fishing communities began noticing changes, not just more fish, but the return of species and size classes that had been absent for years. The restoration project had not been designed to rebuild the inshore fishery. That rebuilding happened because the habitat had come back, and the fish responded to the habitat the way they always had. And then there was the sediment. Mangrove root systems filter suspended particles from tidal water as it moves through the forest. In areas where cleared coastlines had destabilized sediment loads, generating turbid water that reduced light penetration and that accumulated in irrigation channels serving rice agriculture behind the dike. Recovering mangrove belts began improving water clarity and reducing the sediment pressure on adjacent farming infrastructure. A program that began as a sea defense answer was delivering measurable secondary results in fisheries, water quality, and agricultural support simultaneously, without additional budget, without anyone having designed for it. Now, the limitation. Mangrove restoration does not work on every coastline. The results documented in northern Vietnam depended on conditions that are not universally present: appropriate tidal inundation patterns, compatible salinity levels, suitable substrate for root establishment, species selection matched to local conditions, and, critically, the removal of the clearing pressure that caused the loss in the first place. Coastlines where tidal hydrology has been permanently altered by land reclamation, where salinity has shifted through freshwater diversion, or where substrate has been severely degraded may not support recovery even with starter structures in place. Severely altered sites produce partial results at best. The solution worked in northern Vietnam because the underlying conditions for recovery still existed beneath the damage. The system needed a head start. It did not need to be built from nothing. But where conditions allow, the broader pattern confirms what northern Vietnam measured locally. Research cited across peer-reviewed literature and summarized by analysts at The Conversation has estimated that mangrove systems worldwide protect more than 15 million people from coastal flooding annually, and that intact mangrove habitat prevents more than $65 billion in property damage each year. The mechanism is not unique to Vietnam. It operates on every coast where mangroves stand. What the northern Vietnamese experience demonstrated, with concrete measurement and documented maintenance savings, was the price of removing that mechanism and the leverage available when you restore it. The workers still planting along these coastlines today are not maintaining scenery. They are maintaining infrastructure. They monitor the belts for storm damage, replant sections lost to severe typhoon events, manage species composition for the conditions of each zone, and protect growing areas from resumed clearing pressure. This is not a zero-effort system. It is a dramatically lower-cost system, and one that becomes more self-sustaining with each year the forest matures and the root structure deepens. Stand behind one of the restored belts and watch a storm wave arrive. The surface turbulence visible at the outer edge of the forest breaks up within meters as the water meets the first root rows. The energy that arrived at the forest margin as something capable of toppling a person arrives at the concrete behind the trees as a shallow wash. The dike sections behind restored belts have longer repair intervals than the exposed sections nearby. The evidence is not only in the monitoring data, it is in the concrete itself, in the absence of new cracks, in the maintenance crews being called back less often. The sea did not get weaker, the coast did not get luckier. The trees came back. And the trees remembered exactly what to do. What these coastal communities had in the mangrove forest was never background. It was the oldest, most self-maintaining coastal protection system on this shoreline. Alive, rooted in the tidal flat, absorbing wave energy, filtering sediment, sheltering fish, and building its own growing conditions for nothing more than the tidal cycle. When the forest was removed, every one of those functions transferred its cost to concrete and to public maintenance budgets and to communities that had no idea they were paying for a service they once received for free. When the forest came back, those costs began returning to where they had always belonged. The answer was not bigger engineering, it was older engineering. There are coastlines in this situation on every tropical shore on Earth, dozens of countries, every ocean where mangroves grow. The lesson from northern Vietnam is not that every degraded coastline can be rescued by planting trees. It is that the mechanism still works where conditions allow, that the bottleneck preventing recovery is often narrower and more breakable than the scale of the problem suggests, and that the cheapest intervention is sometimes not the one that looks smallest. It is the one that targets exactly the right point in the system at exactly the right moment. $7.3 million a year. Saved by trees that grow in mud, that follow no engineering spec, that required no special design, and that had been standing on this coastline long before any concrete was ever poured. They did not overpower the sea. They hired back the workers they had fired.